Let's look at a basic yielding problem for a steel plate and see if we can obtain values for LRFD, yielding, and rupture. So here in this diagram, you'll see that we have an 8x1/2 inch plate. We are going to assume that it is ASTM grade A36, which means we have an FY of 36 and we have an FU of 58, and these are both KSI values. Now we're only going to check for yielding and rupture in this video because these are the simpler ones to check for, and when it comes to block shear, I'd rather have a full-length video to discuss that concept. So the important things that we're going to look at in terms of spacing on this are we are going to analyze where these bolts are at. So we'll see that we have 6 bolt holes. Most importantly, we have 2 rows, and for this type of problem, that's really what you care about. We aren't looking at any sort of staggered situation. We are looking at loading going right through. It's not like we have something where there's a bolt here, and a bolt here. That's staggered load, and we'll talk about that in a separate situation. Here we have a pretty simple situation. So if we're going to check yielding and rupture, we have 2 equations. We have PU, since we're doing this in LRFD, has to be less than or equal to phi of tension, or tensile, we could say, times Pn, which is the nominal strength. And this splits into 2 separate equations. So we have phi t equals 0.75 for rupture, and we have a value of 0.90 for yielding. And the other important thing that we have to look at in these types of problems is, do we have a shear lag factor? That shear lag factor is U, and we use U in the equation AE, which is effective area, equals AN, which is our net area, times U. Now in this problem, U is going to be equal to 1.0, and if you're curious why, you can go to AISC table D3.1, and it's going to be case 1 in that table. Because we have a flat plate here, we are not dealing with any sort of shear lag. If we had an angle and we had a top leg protruding from either the top or the bottom here, then we would have a different scenario on our hands, but we have no shear lag in a bolted flat bar. So that makes this a little bit easier. So let's look at what our equations are actually going to be. Let's do yielding first. Yielding, we can look at Pn is less than or equal to phi t Pn. We can break this out to say phi t is going to be multiplied by Fy times Ag. Okay, so Fy is our yielding stress. We found that up here, or we know that because of the material that we're using. And Ag for a bar is pretty simple because we have an 8-inch bar by a 1/2 inch bar, and that's going to give us a 4-inch squared gross area. So we can do this pretty quickly. Phi t, we'll say this is 0.90 because we're talking about rupture, or yielding, pardon me. And if we do this out, we have 36 times 4 times 0.9 is 129.6 kips. So we now have our controlling load for yielding. Let's do rupture now. So rupture starts out as the exact same equation, right? If we have rupture, we're looking at Pn, again, has to be less than or equal to phi t Pn, which is going to be 0.75 times Pn. But what is Pn? Pn can be broken down into FUAE, which is slightly different, but we were talking about what this is earlier on. We don't really have to worry too much about this. This is 0.75 times FU times AN times U, but U is 1.0. But how are we going to get AN? Let's take a little side tangent here to see how we're going to do AN. So AN is going to be equal to area gross minus the diameters of the bolt holes. I should say this as the sum of the diameters of the bolt holes times the thickness of those bolt holes, okay? So we have 2 of them, so that's why the sum of them is important here. So we have 4 inches minus 2 times, what is our diameter? I should have probably said this earlier. We have 3/4 inch bolts in this problem. When we go up and we're looking at this problem, we have 2 3/4 inch bolts, but is it only 3/4 of an inch? No, it's not, right? We have to add a 1/16 for roughness and a 1/16 for spacing to get the bolt in. So effectively we have a 7/8 bolt here, and I'm running out of space to write this, but our thickness is 0.5. So the 2 and the 1 will cancel. You can look at that, and the 2 and the 0.5 will cancel. So you have 4 minus 7/8. Yes, 4 minus 7/8 because we're talking about gross area here. So you're going to be left with 3 1/8 is equal to 3.125 inches. And U is equal to 1.0. So PN comes out being equal to, less than or equal to 0.75 times 58 times 3.125. Which, if we look at 0.75 times 58 times 3.125, you have 135.94 kips, okay? So what's interesting about this is a lot of times you'll see that rupture controls over yielding, right? But in this case, when we get these additional bolt holes, we'll see that we actually have more rupture strength available to us. And yielding is actually what is going to control this situation. So our controlling case is going to be yielding with a value of 129.6 kips. And that's it. That is how we do this problem. I hope you found this helpful, and if you did, please leave a like and subscribe to the channel. See you soon.